In this video, we're going to look at organic nomenclature, that is how to name organic molecules. So it turns out that there's this large body of scientists, scholars, a lot of lawyers that develop what's called the Iupac, which is the International Union of Pure and Applied Chemistry. And they have developed a set of very systematic rules for determining the names of organic molecules. Systematic approach to naming organic molecules. And so what their goal is they want to assign one name to a molecule. So it's one name to, let's have one molecule. That was their goal, okay? And they've done a very nice job of it. As a result, though, to get to have one name apply to only one molecule is a difficult task. And as a result, there are a lot of rules to sort of follow. So each molecule now has its own Iupac name, is what we say. So it really, this is a little bit misleading. It turns out that because of the way molecules were discovered, especially those that were discovered long before Iupac was formed, they may have many common names that we say, but the legal name would be the Iupac name. It's not to say the common names aren't helpful, but it's even more helpful for every molecule to have one singular Iupac name. Going back to this definition a little bit, I was very careful in how I worded this when I said we're going to assign one name to one molecule, okay? That isn't saying that every molecule has only one name. It turns out that molecules can have multiple names, okay? But in terms of Iupac, what this is saying is that if you have a name, like you've got a series of letters that form the name of a molecule, that series of letters can only apply to one molecule. So each molecule can have multiple names, like we could have the name acetic acid or ethanoic acid for one molecule. But that name acetic acid only ever applies to one molecule. You can't say acetic acid and describe 5 different types of molecules, or just by accident 2 molecules. No, the letters that I'm pronouncing acetic acid describe only one molecule. If I draw the structure for acetic acid, I could name it a few different ways. Okay, that's what we're getting at. Okay, anyway, let's get to the actual rules for this. So what we have to recognize is molecules can sort of can be depicted in different ways. For example, we could have bond line structures, Kekulé structures, Lewis dot, and Iupac has to work on all of those. But also, as we saw in the previous lecture, we could have a molecule which the Iupac name, conveniently enough, I didn't mislead you, is hexane for this molecule. But, excuse me, conversely, I could have the molecule like this, and I could have the molecule drawn like this. And all of these are hexane because, remember, molecules, they don't care about us. They don't care about our ability to communicate their properties effectively. They are just themselves, molecules. And they can roll around and spin around and kind of twist in on each other in space and be depicted in different ways. That's just the reality, and we have to appreciate that. There's only so much we can do with a two-dimensional piece of paper, but we can get a long ways. And so what we need to be able to do is have a set of rules that describe each of these molecules as hexane. I can say they're hexane because I've got experience with them, but is there a set of rules where somebody with less experience handling these molecules could actually come up with the name hexane for all of them? And there is. Okay. So the Iupac nomenclature rules. And the way this works is not, I don't want to give you all of the rules in one learning module and even in one class. Instead, what I want to do is start with the foundation and look at the foundational functional group, which is the alkane, and then cement those rules as our foundation, but then continue to sort of build on them as we look at more complicated molecules later on in the semester and then into organic 2. Okay, so number 1, we want to identify the parent chain. And what we're doing with identifying the parent chain is looking for what's the longest straight chain. What's the longest straight chain? And number 2, and this is going to get a little bit more vague until we actually start looking for examples. Number 2, we are going to identify and name what are called substituents. So we're going to identify and name these substituents. These are the groups 1, 2, etc. carbon chains on our molecule. So these are like the things that were hanging off of that long chain. So if we had heptane and we cut one of the carbons off and moved it on the inside of the chain, that would be like a 1-carbon substituent. It has substituted for a hydrogen in the molecule. And then step 3 is we're going to add position information for the substituents. Okay, and here's where we say, is it attached to C2, 3, etc. This is where we're telling ourselves we have this 1-carbon substituent hanging off of our main chain. Where is it connected on the molecule? Is it at C2? Is it at C3? Because those are different and we need to know. And then the last thing that we do is we add prefixes to determine the number for each substituent. If you've had chemistry before, you will be familiar with these prefixes. You will not have used them in this context, so it's not a big deal if you haven't seen them, but this is where we get into di, tri, tetra. So if you name molecules as like magnesium dichloride, magnesium chloride would be better, but magnesium dichloride, carbon monoxide, carbon dioxide, there we go. Carbon dioxide, aluminum trichloride. Okay, that sort of thing we're going to use on our various substituents. So let's actually, before we look at an example, let's look at our substituents. Okay, so what I'm saying is that, let's say we've got this chain that goes on forever. We could have groups hanging off of our molecule, our parent chain. So here, here, here. Now, what again is our parent chain? Our parent chain is the longest chain in our molecule. And this is one we haven't learned the name of, so I'm not going to worry about it. And I don't even like clarify it. My point is the number of carbons in the purple chain is way more than the number that are in each of these individual yellow chains. The yellow chains are our substituents. So we have if you look, we have a 1 times C chain, 2 times C, 3 times C, and 4 times C. For example, it could be variable numbers. It turns out you can't really get, for the ones we're going to look at, it's hard to get higher than 3, because if you get higher than 3, you start to change what, in this case, is the purple chain. That is the longest chain in the molecule. Okay, so what I'm going to do is I'm going to draw a rest of chain kind of break. So this would be what a 1-carbon chain would look like off of our parent chain, the rest of the parent chain. We could have something like this. Said another way, that's CH2, CH3. Remember, carbon only wants to be bonded to 4 things. Okay, so these two are the same. And then we'll stop at 3. You'll start to get the idea. Well, now we can go on to 4. Okay, so this parent chain, excuse me, this thing that's attached to the parent chain has 1 carbon. It's a CH3. 1 carbon. And so what we're going to do is we're going to rely on our knowledge of things that also contain 1 carbon. If you recall, methane has 1 carbon. But what I'm going to do is I'm going to cross out the ane because it's not an alkane. This is not methane. Methane is CH4. But what I'm going to do is add the suffix YL. And collectively, this is METHYL, or methyl, 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 okay? So that is a methyl substituent. Okay, we could do the same thing over here with 2 carbons. We're going to take ethane and we're going to cross out the ane and we're going to add in YL, and that's going to give us an ethyl substituent. And similarly, this is going to be 3 carbons and it's going to be a propyl substituent and a butyl. Now we can keep going, a pentyl, a hexyl, a heptyl, a nonyl, a decyl. Sure, but it turns out, like I said, the longer the substituents that you add to your chain, you're going to actually change the parent chain. And that's going to screw things up a little bit. Okay, so these are our substituents: methyl, ethyl, propyl, butyl. And then we can start to see how these things apply. It turns out that this molecule has an Iupac name of ethanol, or somebody could call it ethyl alcohol. Whenever we add an OH to a molecule, we change that molecule into an alcohol functional group from an alkane. Okay, let's get into an example of this. So if we, let's do this. Good, okay, this is a great example. So what we want to do is step 1, parent chain. So the parent chain is going to be the longest straight chain hydrocarbon in the molecule, the longest straight chain fundamental alkane. So what you could do is, I'm going to kind of copy this. Sorry. Man, you'd think this would just be easier. There we go. Okay, sorry, I'm back. Okay, so the longest chain looks like this, and that's going to be 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. Similarly, we could go 1, 2, 3, 4, 5, 6, 7, 8, and that's 8 carbons. I was careful about my example. It won't matter which of these two we choose to be our parent chain, we would get the exact same answer. I could have made it more ambiguous, but I will be careful. So I could have made it so there was like this weird tie, and then you're like, it could be 2 possibilities, but there is only one. There can be only one, and Iupac has an answer, and I don't want to overwhelm you with rules, so we won't get to that. But so those are 2 possibilities. If instead you said, what if you were like, What if you were like, you know, maybe this is the longest chain. No, 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 that's not the longest chain. Similarly, this is not the longest chain. You have to get the highest number possible. This one isn't too bad because we could have just gone from left to right and seen it. There are some that can be more complicated. Okay, so we're at 8 as our parent chain length. That is our longest straight chain hydrocarbon. What that means is that this molecule is an octane. Octane. Okay, now for the substituents. Look at that, getting faster, getting better. Okay, the substituents are here and here. This first substituent is ethyl. The second substituent is methyl. The reason why this one on the left has 2 carbons and this one on the right has 1 carbon. So step 2, we've identified and named the substituents. Now, step 3, we want to add the position of the substituents. So if we, again, number, what we want to do is number the actual parent chain. And here's the caveat. This one is where it gets a little bit tricky. We want the lowest numbers possible. The lowest numbers possible. So this one's not too bad. We've got 3 and we've got 5. What I mean by lowest numbers possible is count left to right and right to left. And then if there's like a vertical component to it, you want to go up and down and up, just to make sure you get both kind of approaches. So my point in this is, instead of going 8 over here, we could go we could go 8 on the left side and 1 on the right side, and that would give us a 6 for the ethyl group and 4 for the methyl group. So over here we've got 3 ethyl, 5 methyl for that high example, and then at the bottom we've got 6 ethyl and 4 methyl. Hopefully you see that. Now the star goes to the one with the lowest numbers. Sometimes it's harder to tell. I mean, sometimes it's harder to tell. It's a little bit confusing. What you can do is you can use the sum. If you're not sure which number is lower, which number set is lower, Iupac says compare the sum. That is, in our first case, we've got a 3 and a 5. So 3 plus 5, that's equal to 8, versus a 6 plus 4, that's equal to 10. This is then the approach that we want to use. That has the lower set of numbers. That sum approach is very useful if you have more complicated molecules. Okay, so I believe in step 4, we would add di, tri, tetra, but that's not applicable in this particular example. There's only 1 ethyl group and 1 methyl group, and we don't add mono. Okay, so no mono. So what this means is now we are ready to do a name, and what we're going to do is we're going to do number, substituent, and then we're going to do parent. Number, substituent, parent. There's no space between the substituent and the parent, and there's always a hyphen between a number and a letter. So what does this one look like? This, I believe, let's remind ourselves, we had 3 ethyl, 5 methyl. 3-ethyl, 5-methyl. Those are my substituents. Notice they're also listed in alphabetical order. If it was 5-ethyl and 3-methyl, it's not the numbers I pay attention to. It's always the alphabetical nature of the substituents, where you put the, you prioritize based on alphabetical. And so ethyl always beats methyl. And in that case, I'll mention it now and I'll mention it elsewhere. You ignore the di, tris, and tetras. So if you had dimethyl, for example, which we can look at in the next example, if you had dimethyl, that would not change. That would not change whether you put methyl or ethyl first. Ethyl is first because it is E and it comes before M in the alphabet. Okay, so we have 3-ethyl, 5-methyl. Notice my hyphen usage between all numbers and letters. And then octane. And there's no space between methyl and octane. And the no space isn't a big deal, but as molecules get more complicated, you want to use some spaces for some functional groups. And so me pointing out when to and not use spaces can be helpful. All right, let's look at another example. So this, I should add, this is done. That's the correct answer. Okay. Just give me a second. I'm trying to make this intense. All right, hard one now. So, got this janky molecule. We need to figure out how to name it. So, let's first ID the chain. Well, here's what I'm going to do. I am going to copy this and then go on to the next page so that you can write it down and you have a blank slate, I guess, to work from in case this is a tough one to draw. And this is a tough one to draw. That's okay. We'll make it. So here we go. All right. I know where the longest chain is. And it's going to take a little bit of practice to be able to see this as quickly. But that's going to be the longest chain in the molecule. Now, similarly to a previous example, we looked at if you've got a situation like this where you've got methyl groups or 1-carbon chains hanging off right next to the end, it doesn't matter whether you start from here, here, or here. Just to emphasize that, I'm going to make this a little bit more awkward of an angle. Okay, so that's my longest chain in my molecule. No matter how you bend and twist, you cannot get longer, you would only get shorter. And we don't want short, we want the longest chain possible. That's what Iupac says. So I'm just going to count off. I'm not going to worry about which side of the molecule I start on. I'm just trying to get the parent, and the parent is heptane. Okay, so step 1 complete. Step 2, which is our substituents. Okay, our substituents now are the things, maybe I'll pick a different color. Substituents are the things hanging off of the parent chain. So everything else was highlighted yellow. Okay, so what we notice is that we've got a 1-carbon chain, a 1-carbon chain, a 1-carbon chain, a 2-carbon chain, 1 carbon, and 1 carbon. Whew, all right, how many 1-carbons do we have? It looks like we've got 5 1-carbon chains or 5 methyl groups, methyl substituents or methyl groups. And then we have 1 ethyl group. Okay, so now 3, we want to add the positional information. So I'm going to have kind of two versions of this. I could start at either end of the chain and go 1, 2, 3, 4, 5, 6, 7. Or I go 1, 2, 3, 4, 5, 6, 7. In which case, I would have a C2, C2, C3. I don't know what the best way to draw that is without kind of confusing with how many carbons we have. Maybe I'll put number 2, number 2, number 3, number 4, number 4, number 5. I believe I captured them all. Now that's going to be in contrast. So that's a 2, 2, 3, 4, 4, 5 system. And if you, there's a lot of numbers. Let's not overthink this. Let's just add this up. 2 plus 2 is 4, plus 3 is 7, plus 4 is 11, plus 4 is 15, plus 5 is 20. So that's my sum total. Now, if I go in the opposite direction, I'm at 3, 4, 4, 5, 6, 6. Okay, so it's 3, 4, 4, 5, 6, 6, which is, I believe, much higher, but let's do the math anyway. So 3 plus 4 is 7, plus 4 is 11, plus 5 is 15, plus 6 is 21, plus 6 is 27. Okay, so I'm glad we considered it. It was probably pretty clear that it was going to be the alternative route, but now we have our numbers. So we have our positional information. We have our substituents. Now let's throw everything together. That is in this next step, which I believe is step 4. We're going to add di, tri, tetra. So what did we have? We had 5 methyl groups. Pentamethyl. If you have 5 methyl groups, you need 5 numbers. What were those numbers again? Those numbers correspond to the positions of each of the methyl groups. If you look, we had, let's go down here. We had 2s. We had 2 methyl groups at the 2 position, 1 at the 3, 1 at the 4, and 1 at the 5. So this is going to be a 2, 2, 3, 4, 5 pentamethyl system. Couldn't be more complicated. 2, 2, 3, 4, 5 pentamethyl. No space. Okay, notice we have commas between numbers. And I've got 5 numbers to match the number 5 for the various methyl groups. If you've got 5 methyl groups, you need to have a number corresponding to where each of them is located on the parent chain. Now, similarly, we're going to use those positional information again to find the ethyl. That's at position 4. So it's going to be 4-ethyl. And now we can start to piece this together. So ethyl always goes before methyl. It doesn't matter how many we have. And that's important because if we had dimethyl, right, D would seemingly come before E, but we don't count the di, tri, tetra, penta prefix. And I should say it's tetra for 4 times something, and it's tri for 3 times something, just in case you haven't seen it before. Sorry, I didn't. And then di for 2. Penta is pretty bonkers to get that high, but I like to throw a hard example in front of me so you can see how I approach solving it. So 3, 4, 5 pentamethyl. No spaces, hyphens between numbers and letters, commas between numbers, alphabetical. Just made one typo at the outset here. That's why you check your work. I'm just going to rewrite that as ethyl. Excuse me. and then our parent chain, which was heptane. Okay, so that's naming a straight chain hydrocarbon. There's two of them. We could also do the exact same thing for rings. Rings are a little bit easier in some respects in that for naming rings, it turns out that in step one, the steps are very similar, but in step one, the ring determines the parent. Okay? In step two of naming, it's the same. In step three, which was the positional information, is it attached to C1, 2, 3, 4, 5, 6? You define C1 to give the lowest numbers. So that's where this is a little bit different, because before C1 was just one end of the chain, one end of the chain, or the other end of the chain, left, right, up, down, just one of the ends, one of the caps on the chain, if you will. Here with a ring, it's just bigger. So for example, if we had, if it's a ring, it doesn't have like a true end. Okay, so what we need to do is pick one of those carbons to be C1 as we name the thing. So this is a good first example. So in this example, we'll first identify the parent as cyclohexane. Parent cyclohexane. Then we have 2 times methyl groups. Okay, now we pick where carbon 1 is. I'm just going to draw a bunch of these. Okay, it often makes sense to put carbon 1 as the place with the substituent. So let's let that be a 1, carbon 1. Now, the next carbon that it's going to be 2 has to go around the ring. So it's either going to go 1, 2, 3, 4, 5, 6, or we could go 1, 2, 3, 4, 5, 6. So after you define where carbon 1 is, it's healthy to kind of roll around the ring a little bit. Okay, so I said that I want to have that be carbon 1, so then I would have, if you look at this name, I would have 1, 2 dimethyl, just throwing that di prefix in front of the 2 methyl groups. Now that's probably the best one to go with. It's 1,2-dimethyl cyclohexane is the name of this molecule. But let's look at some other numbering strategies so you can see where you could go wrong. So going the wrong way around the ring, this would be 1,6-dimethyl. If we add up the numbers, 1 plus 6 is 7. That's bigger than 3, which is what we had in the other example. If you pick the wrong place to put 1, you're kind of setting yourself up for difficulties. This is 3, 4. That's not going to work. And then like you could make it really bad and go up to 11. And so with 5, 6 dimethyl. Okay, but if you instead went, in this particular example, this is where rings get a little tricky, and this is where I'm super careful in the questions I ask. This would be 1, 2. If you went 1, 2, that would be the same. And so the name of this molecule is 1,2-dimethyl cyclohexane. All right. What if there's a tie? What if there's something like this? What if there's a tie with different, let's split it up a little bit. Mix it up. What if there's a tie with different substituents? Okay, so I've drawn a cyclopentane. Now, is it 1 ethyl, 3 methyl, sorry, or is it 3 ethyl, 1 methyl? So which of these two is it? And it turns out it's this answer. And we say priority goes to the bigger group. So priority goes to the bigger group if you've got a tie in that situation. Priority goes to the bigger group, but lowest numbers always prevail. So when it comes down to numbering the giving substituents the lowest numbers possible always is always better than having a than the priority issue. So for example, what should we do about this molecule? And I'm just going to check to make sure. I feel like in the past I've said this wrong, so I'm just checking. I've got a computer program. The details of nomenclature sometimes can escape everyone, and it's better to check to waste somebody's time, I guess. Oops, sorry, than to check. So I'm going to draw this molecule. You think through it, what you think it should be based on what I just said, where the lowest numbers prevail. And then I am going to, yes, the lowest numbers prevail. So for this one, I was right. I just wanted to make sure. It turns out when I wrote this last year, I was wrong. Okay, and the student corrected me. So let's work through this. The lowest numbers prevail. So this is the bigger group. And by that, I mean the ethyl group is larger than the 2 methyl groups. But it turns out that you would call this a 2-ethyl 1,1 dimethyl cyclopentane, as opposed to giving the larger ethyl group the priority and calling it 1 and then 2, 2, ... Because if you did that, if you did that, 2 + 1 + 1 = 4 versus 1 + 2 + 2 = 5. And so that's going to make this lower approach to be incorrect. So I mentioned, I know this is a lengthy lecture, nomenclature is just fairly lengthy. I mentioned that you could use this to help you resolve issues with constitutional isomers. Okay, definitely true. So one really unfair question. I mentioned last time that I could say, draw all constitutional isomers of like pentane. That's pretty boring. It'd be like hexane or heptane, one of those two, maybe octane because it's take-home test anyway. But I wouldn't do anything else than that. You might be thinking like, okay, heptane, sure. What about cycloheptane? Well, let's just make it simple. Let's talk about cyclopentane. Pentane itself was quite simple, right? So pentane, it turns out, has this and this for C5H12. Sorry, again. Those are the only 2 constitutional isomers in addition to the parent molecule. So we have 3. Pentane has 3 constitutional isomers. That's probably too easy for a take-home test. And cyclopentane is probably the same, right? Actually, no, because the rings can get smaller. Okay, so we could have a 5-membered ring. We have one possibility. We could have a 4-membered ring. That's another possibility. We could have a 3-membered ring like this, and we could have a 3-membered ring like this. We could introduce double bonds if we wanted to. Right? Double bond there. Double bond there. And there's actually even more double bonds. So that's not really a fair question. Instead, what I would do is I would say, okay, which of these is a constitutional isomer of cyclopentane? So here, don't list all, Don't worry about listing all. But do be able to recognize constitutional isomers. Okay, so let's look at an example of that. Let's say we've got heptane. This. This. Okay. So what I want to do is let's name all of these structures. So this one is heptane. Now let's break down B here. So added a carbon. The longest chain is going to be here, and that's 5. So this is going to be 2,3-dimethylpentane. Okay, so there's 2,3-dimethylpentane. All right. Okay, now we once again have a pentane, 5-carbon chain is our longest chain. That's going to be a 3,3-dimethylpentane. A little crowded here. And then this last one, maybe you can see, is also a 2,3-dimethylpentane. So if we follow the Iupac rules, we can get a collection of molecules. And if we get pretty fast about this, we can see when molecules are constitutional isomers and when molecules are duplicates of each other. So if you were listing the constitutional isomers of heptane, you were just drawing molecules where you made sure that the carbon-hydrogen count was correct, what you would do is you would kind of write all of these, and then at the end of the day be like, ooh, shoot, I'm checking my work. This one is a duplicate. It has the same Iupac name as the second one here, 2,3-dimethylpentane. 2,3-dimethylpentane is one constitutional isomer of heptane, but all of the different ways of drawing 2,3-dimethylheptane get into duplicates. So a long lecture, but a foundational lecture. And if I'm honest, I don't get super excited about nomenclature. I'm not sure too many people do. It falls into kind of the realm of like taxonomy in biology, if you're familiar with that, where you're kind of naming genus and a genus and attaching a genus, species, maybe even phylum, kingdom, a bunch of stuff I kind of remember. You know, it's clear as you get into the field why that's useful, but when you're learning it, you're like, this isn't what I signed up for. But trust us when we say learning stuff like this is useful and is beneficial because it allows us to communicate effectively about the molecules that we're working with. And good news, we kept it to one lecture. So we're done with constitutional isomers and we're done with nomenclature. We're going to move into the last topic of module 2, which is starting to depict something called conformational isomers. Okay.